Hello everyone. Welcome to Electronics Workshop. Today in this video we are going to learn about operational amplifier. I am planning to make a complete series on this topic, operational amplifier. This is the first video of our OpAmp series where we will be talking about introduction to operational amplifier and deal with characteristics of ideal OpAmp. In the coming video we will go in detail about OpAmp along with their practical examples. So, stay tuned in my channel if you want to learn more about operational amplifier. Now, let us go through the video in detail. An operational amplifier is an integrated circuit that is basically used to amplify weak electrical signals. Op-amp are used extensively in filtering, signal conditioning or to perform mathematical operations such as addition, subtraction, integration and differentiation. Operational amplifier are connected to various circuits in order to perform variety of operations. The first one that we will be talking about is amplification of input signal. When we combine a op-amp in our amplifier circuit, it amplifies weak input signal to strong output signal. We may be confused in why we need amplification of our signal. To make it clear, you can just go through this image. In embedded systems or in electronics, we need to measure output signal of different analog devices like sensors. Sometimes the output signal from these sensors are very small in the range of few millivolts. These output signal are not correctly measured by a microcontroller unit. So we use operational amplifier to amplify these signal and make it fall in the range of measurement of microcontroller unit. So that microcontroller can measure the output from any analog devices accurately. Operational amplifier are also used in elimination of noise from the input signal. By operating as a filter of input signals, the operational amplifier circuit is able to extract the signal with the target frequency, eliminating all the other frequency entering MCU. From the figure we can see that there are many sources of sound that combines with the input signal. If we use that signal without filtering, then our MCU cannot recognize the exact input signal. So, using operational amplifier as a filter, op-amp circuit is able to extract the signal with the target frequency, eliminating all the other frequency entering MCU. This is the symbol of operational amplifier. It has two input pins, two power supplies, and a single output pin. The two input pins are named as inverting terminal and non-inverting terminal as they function. We will figure out the different output that we receive after applying different input signal in these input terminals. Operational amplifier behaves as a differential amplifier that amplifies the difference in the input voltage and provide it to the output pin. Suppose, if V1 and V2 are the two input voltage of the operational amplifier and A is the gain of that amplifier, then the output will be A times V1 minus V2. If Vd is the difference in the input voltage, then the output will be Vd times A, where A is the open loop gain of the amplifier. The meanings of open loop gain is the internal gain of the operational amplifier without any external feedback in the circuit. The open loop gain of operational amplifier varies from 10 to the power 5 to 10 to the power 6. That is a very large number. This clearly means, if we only apply some millivolts voltage at input, we will receive 1000 of volts at output. Which doesn't seem much practical. So the output voltage can be controlled with the help of this bias voltage V plus and V minus. The output voltage swing of the op-amp cannot exceed the bias voltage limit. Let us see this by a practical example. We have taken an operational amplifier and grounded its inverting terminal and applied 100 mV DC signal at non-inverting terminal. We set the upper bias voltage V plus to 1 MV and lower bias voltage V minus to minus 1 MV. We also set the op-amp gain to 10 to the power 5. Then our output voltage will be 100 kV as shown in the figure. Now we will perform for some analog voltage. We just remove our DC power supply and add AC power source with amplitude of 1 volt and frequency of 100 kHz. The blue curve is representing the output and green line is representing the input. From the figure we clearly see the input as 1 volt is amplified to 100 kV in the output. To see it more clearly we will decrease the bias voltage to plus and minus 5 volts. So, let's see the result, what happens. Oh, that's pure square wave at the output side although they're analog wave at the input. Now, we will see how is that possible. This is possible because open loop gain of the amplifier is so high that it amplifies the small positive voltage to 100 kV and small negative voltage to minus 100 kV at output. To see it more clearly we decrease the open loop gain of op-amp to 2 volt. That mean to say if we apply 1 volt at input, we will get 2 volt at output. Wow! The curve looks great and very much clear. The input analog voltage is 1 volt peak, clearly represented by green curve and output voltage is 2 volt peak, clearly represented by blue curve. Now we will know about the voltage transfer curve of op-amp and understand it practically. We have set open loop gain of operational amplifier to 2 volt and the bias voltage to plus minus 5 volt. We will increase the input voltage to 2 volt to see the respective output voltage. Great. The output curve looks fine. We further increase the input voltage and make it 3 volt to see the output. Now, the output has changed. Our input voltage is 3 volt and gain is 2 volt. By a simple calculation we know the output that must be of 6 volt. But we have set the bias voltage to plus minus 5 volt, so once the output reaches the bias voltage that is 5 volt in this case, it gets saturated to the bias voltage in both the negative and positive side. So we can compare the input and output curve. The input curve is fine analog signal but the output gets saturated once the voltage 5 volt which is the bias voltage applied to operational amplifier. And this is called the voltage transfer curve of op-amp. I think we are clear about the basic operation of the op-amp. Now we will go through the equivalent circuit of operational amplifier. The equivalent circuit of the ideal op-amp looks like this, in the figure. Ri represents the input impedance of op-amp and Ro represents the output impedance of the op-amp. We already know that output voltage equal to the open loop gain multiplied by the difference in the input voltage V1 and V2. Now we will see the characteristics of ideal op-amp. Infinite input resistance. The ideal op-amp draws no any current through it. So, no any current flows in or out of the input terminals of the op-amp. To maintain this condition, the input resistance of operational amplifier must be infinite, which is proved by a simple Ohm's law equation as shown in figure. In practical cases, we cannot get infinite input resistance. The input resistance come in the range of megaohms. But in this case we are discussing about ideal condition. Zero output impedance. In the above figure, RO is the output impedance, which value must be zero in the ideal case. Although the output impedance cannot be zero in practical case, we can minimize it, so that we can get the maximum voltage across the load connected to the output terminal. Infinite open loop gain. The open loop gain is the internal gain of the operational amplifier without any external feedback. The open loop gain of OpAmp must be infinite ideally. In practical case it ranges from 10 to the power 5 to 10 to the power 6. Zero output voltage when the input voltages are zero. As we know, the output voltage of any operational amplifier is the difference in input voltage multiplied by its gain. If the input voltages are zero, the difference in input voltage is also zero. When zero gets multiplied by the gain of the amplifier, the output voltage should also be zero. Infinite bandwidth. The meanings of the infinite bandwidth is, the operational amplifier must support all the frequency, ranging from 0 Hz to infinity. Beside these characteristics, the very important characteristics of operational amplifier are slew rate and common mode rejection ratio. I am just explaining the basic of these characteristics in this video. I will be making a separate video covering this topic in the coming videos. Now let us learn about slew rate. Slew rate of any operational amplifier is defined as the rate of change in output voltage due to step change in input voltage. It is also defined as how fast OpAmp is able to respond to the input voltage. The figure shows the slew rate characteristics of operational amplifier, where the input is pure square wave but the output reaches the maximum amplitude only after time del t. For the ideal OpAmp, this change is time to reach the maximum voltage must be zero. That mean to say, the applied input voltage must appear at output instantly at zero time. So, for that, slew rate must be infinity for ideal OpAmp. Common mode rejection ratio. The common mode rejection ratio (CMRR) indicates the ability of a differential amplifier to suppress signals common to the two inputs. As shown in the figure, in the single-ended OpAmp, when noise appears in the input, it gets multiplied with the gain and appears at output, which is not so practical, and our original signal get distorted. But in case of differential amplifier, the same amount of noise is input in the input terminal. If the amount of noise is exactly same, it gets subtracted and we can get pure output signal without any noise combined with it. The function of the common mode rejection ratio is specifically used to reduce the noise on the transmission lines. So this common mode rejection ratio means how well OpAmp is able to reject its common voltage applied at input terminal. In ideal case, common mode rejection ratio must be infinite. These are the ideal characteristics of operational amplifier. Here, we see the comparison of ideal OpAmp with the practical OpAmp. You can go through each point in detail. The detailed documentation of this video is also provided in my website. I have attached the link of my website in the description box. I think it may be useful for you if you once go through it. We will also see in detail about each characteristics in coming video. So if you like our content, stay connected to our channel for more such videos.